thanks a lot for having me virtually at McGill. I'm very happy to be here and to present you a recent work that we did that is published in this journal. So feel free to go there and check more about it. So the title of my talk today is Variational Annealing. I hope all my slides are okay. I'm kind of using 2 screens here, so I hope the combo is working. Just let me know if something's wrong. All right, so typically when we talk about variational annealing, what we have in mind is optimization problems, like solving optimization problems. And optimization problems occur in different segments in industry or as well in science, of course. So here I have a couple of pictures that describe a couple of different things here. For example, we have a representation of the so-called traveling salesman problem. It's a problem of finding the shortest path for, say, a businessman traveling to cities once, and yeah, you want to minimize that path, right? And so this is one of a typical optimization problem. Another one, which is pure in quantum chemistry stuff. So imagine that you have like a couple of atoms interacting via some potential. So usually what you're looking for is to find a configuration that minimizes the energy, and usually that configuration is in a local minima. Another optimization problem is so-called protein folding, where you want to know the conformation of a protein going from an unfolded state to folded state or a native state, where the protein is functioning. And typically, the pathway to that is going through like an energy landscape of a couple of minima, probably Southernmost as well. Another problem, which is not at all in the other ones, in finance, for example, we have, say, the problem of portfolio optimization, which is a problem of finding the best way of allocating the assets in your portfolio, right? And many more, right? But now you can ask yourself the question, why, as a physicist or a statistical physicist, am I interested in problems that, yeah, some are kind of, they have a physics flavor, other are totally very far from physics. So the reason why people are interested in that is that most of this problem could be cast into a form that the physicists understand. And this is the form of an Hamiltonian, right? Where the specifics of the problem are encoded in the interaction between the so-called spins variables that are binary, usually 0 or 1. And yeah, the form of this interaction usually encode the specifics of the problem. And solving that problem is simply finding the minimum energy or the configuration that minimizes that energy functional, right? What we usually call as a ground state. And so we can use, once a problem has been formulated this way, we can use all the techniques that we've been developed for years to find a ground state of classical Hamiltonians. But there's a catch. The catch is that some of those problems are very hard. So for example, there's the so-called disorder Ising glass in the random non-linear field. Finding the ground state among the 2 to the n possible solutions is NP hard. So typically people kind of relax the ideal reach of finding exactly the ground state, but to find an approximate solution, a good enough solution, right? And that's where they have to design heuristic methods. And as a physicist, it's usually intuitive for us to view this energy functional as a form of a landscape. For hard problem, it's usually rock, exponentially large number of minima at points. And solving the optimization problem means finding the deepest value in the landscape. For approximate solution, like a low-lying value. Right? One of the methods that have emerged in finding approximate solution is a so-called simulated annealing or thermal annealing problem, whereby you devise a search algorithm that uses thermal fluctuation to explore the barriers until you find the global minimum, literally, right? And this is inspired on a very old metallurgical technique, whereby to make a material durable, you heat it up. By heating it up, you give it thermal energy. The atoms are moving everywhere. They basically can explore high energy states, and then you slowly cool it down. And by slowly cooling down, the atoms in your material, they rearrange themselves in a configuration that minimizes their free energy. And so what we do is that we simulate that kind of thermal process, right? And it has already been also been implemented on kind of dedicated that way, like Fujitsu, a little bit like people accelerate now machine learning on GPUs, right? So people want to accelerate this kind of simulated process on dedicated hardware. Now, another paradigm whereby to explore this kind of landscape, instead of using thermal fluctuations, you could use the so-called quantum fluctuations, because at the quantum scale, a very, very small scale, nature behaves in a very funny way. And one of the funny ways in which it behaves is that you are able to tunnel through a barrier without overcoming it by using the so-called quantum tunneling effect. And so if you design a search algorithm that uses quantum tunneling, searching for the deepest value in the barrier, hopefully it will be more efficient than the thermal process, right? And that has also been implemented on dedicated hardware. Now you could ask myself the question, okay, what is the most efficient method? We don't know, because in principle, we don't know for a typical optimization problem, what is the form of this landscape, right? But it has been seen that mostly quantum annealing has an advantage, but it really depends on how tall the barrier is, how wide it is, right? But the point I would like to make here is that, is there a question? No, okay, no question. So the point I want to make is that usually people have been simulating both of these phenomena, both classical annealing and quantum annealing, on what we call classical computers. That is whatever you are using now to tune on this so-called, right? And they have been simulating it using the so-called Monte Carlo methods, both for classical system and quantum systems. So these are just some papers, but there's really a zoo of different kind of Monte Carlo methods that people use to simulate either quantum annealing or classical annealing. The point I want to make with this slide is that these methods were initiated to study the properties of classical system at thermal equilibrium or quantum system. They were not used for quantum annealing, but they were repurposed in order to solve optimization problems. So we had in our mind that, okay, we also know some methods that are becoming very popular and very efficient that use neural networks, and they are using it right now or at the time to simulate also or to probe the quantities, equilibrium quantities of either classical system, like in this case, with variational autoregressive network, or quantum systems with restrictables of machines. So we thought that, okay, can we repurpose these methods that use assured neural networks to simulate the annealing paradigm? And so that's the answer that we are giving this talk. So to do that, I will start by having a technical slide, maybe the only technical slide I have this talk, on what is actually the bedrock of the method that we're using. It's based on a so-called variational Monte Carlo method. The fancy term, just to explain a very simple method, the quantum Monte Carlo method. So it's a Monte Carlo method that simulates properties of quantum system at zero temperature. So the particularity of the variational Monte Carlo method is that it finds good approximations of the ground state wave function of a quantum system by minimizing the so-called variational energy. The variational energy is just the expectation value of a quantum Hamiltonian over that variational state. It could be any kind of ansatz. But thanks to the variational principle, we know that this property is always an upper bound to the true ground state energy of this Hamiltonian. So you only have to minimize it, basically, to find a good approximation of the ground state energy. Right, so we replace the quantum mechanical expectation value. So this is, for those who are not that familiar, it's kind of a Dirac notation for quantum mechanics. But yeah, we kind of replace it with statistical expectation values, where all the summation of our exponential states are gone, with some of our polynomial number of states, where each sample here is drawn according to the absolute value square of the probability distribution, that is absolute value square here of the answer that we chose, right? Over some quantity which is called local energy that is given by this formula, basically. Right, and here we assume that we are using important sampling. So we are only sampling configurations that have dominant weight on this integral, which is very important. And the way we optimize the answer, if you just take this formula, you take the derivative, you have this exact formula for the gradients, and we just replace these quantum mechanical expectation values with, again, statistical expectation values, right? And we minimize each parameter in the ansatz by whatever flavor of optimizer that you want, like stochastic gradient descent momentum, stochastic reconfiguration add-on. Yeah, usually stochastic reconfiguration is kind of the way to go because it kind of takes into account the geometry of the the answer you're looking at. All right, but one of the issues that we have when we are using this kind of method is how do we choose the answer? This answer, it needs to be powerful enough, representative enough. You should be able to sample from it very well. So the choice that we had for this talk or for this work was neural language models. Neural language models are very powerful probabilistic models that are able to capture intricate correlation among words in the language, right? And you're able to, giving some words, you're able to sample like next words, basically. And I believe that all of us are kind of using it nowadays almost every day, right? When we write emails. So a very vanilla explanation on how this will work for, let's say, recurrent neural network ansatz is that, okay, suppose that I have like the names of people I want to write the email, the subject of my email. I have some encoding of that. One encoding if it's crazy, or maybe some vectorized, very smart encoding of that. I pass it through my RNN cell and I'm able to predict the first word in my email. So basically what we've learned is just the conditional probability of predicting the next word, giving an input. And you use that next word to predict the next word in your sentence, right? And so on and so forth. So what you've basically learned is a bunch of conditional probability distribution. And you could immediately see that if you take the product of those conditional probability distribution, you've learned the conditional probability of sampling the first sentence your email giving this input. Okay. Now, why is it interesting for physical systems or quantum systems? So suppose that instead of sampling sentences or words in a sentence, I'm interested in sampling instead a spin configuration or a bit string, because this sigmas could be a qubit, like 1 or -1, or spin -1, or a bit string 0, 1, right? And I want to sample a bunch of them. So you could use the same principle, ancestral sampling, as they call it, to basically sample one spin at a time, right? And when you sample one spin at a time in this autoregressive fashion, again, you have a bunch of probability distribution that when you take the product, give you the joint probability distribution of sampling your spin configuration. And for quantum system, basically, typically the wave function is just the square root of the probability distribution, right? So in this case, the hidden state, the H is, the so-called hidden state. It equals correlation among spins in your systems, right? It is, this kind of ancestral sampling is actually exact. There's no autocorrelation time, it's directly parallelizable. And this is very important compared to Monte Carlo methods, because, and this is one of the reasons why we chose autoregressive neural networks, because if we had something like a CNN, convolutional neural network, graph neural network, we cannot sample like that. We need to design some sort of Monte Carlo update. And for Monte Carlo update, you need to build a Markov chains, and Markov chains have memory. You need to wait a certain amount of time for it to be memoryless and stuff like that. So it takes time. It takes more time. Whereas here, the exact sampling is really good, especially when we have seen systems that have that are glassy, right? The relaxation time is even longer. So we found that the recurrent network was good for kind of system we're interested in. Plus, by construction, usually the last layers is kind of softmax. So by construction, your probability distribution is normalized to unity. And we see that it's kind of important. We don't have to compute the normalization factor that is also computationally expensive. So next, what are the RNN cells? So we use a bunch of RNN cells, and we discovered that actually, depending on the structure of the problem Hamiltonian that we're interested to solve, different RNNs have different effects. So for example, here we have what we call the tensorized RNN cell. But before talking about tensorized RNN cell, this structure, let me remind you about the vanilla RNN cell, which has this kind of recurrent relation, right, between the two hidden states. That's a recurrent formula. You have this concatenation between the hidden state and the current input, or what we call local Hilbert space here. And then you have this matrix vector multiplication plus a bias. So these two are like the weights and biases of your neural network cell. But we found that, so this is a nonlinear activation function of your choice. So we found that the hidden state and the local Hilbert space, they only interact via this whatever activation you choose, very low, a low, whatever. right? But we found out for quantum systems, it was better to have kind of, or classical systems, if you want, it's better to have some sort of compact interaction between the two. So we chose this kind of tensor interaction between the two before increasing the representation by some sort of nonlinear function. So we found that this to be more powerful than that. And you could ask me, yeah, we try fancier stuff like GRUs, LSTMs, but we also found that tensor ironing was better. For example, we had this example on quantum Ising chain, some sort of physical system that is hard to solve at criticality, at the critical point where we have phase transition for honest spins. And this is the variance of the local energy of the system. And the smaller it is, the better things are. We see that tensor iron encodes converge faster, and they are actually have a better accuracy than binary irons. And we are the same thing for GRUs on LSTM. So we kind of use tensor iron almost everywhere. Another thing that we notice is that typically for machine learning, when people use recurrent neural networks, you have this so-called weight sharing, right? So here for Rn indices are spin systems. Usually if you have temporal data, it's going to be time, right? And usually you use the same weights and biases among time sequence. But since the interaction between the spins are different, usually they're random, right? For random systems, we found that it was basically better to have different parameters for each lattice size. And when we do that, that's what we call no weight sharing. We indeed see that it's way much more efficient to encode the no weight sharing instead of the weight sharing, where we are basically not able to train when we use weight sharing for this specific kind of system. So you already see that the structure of your iron cell really is dependent on the kind of problem Hamiltonian you're trying to solve. It's kind of similar to the fact that we know that, okay, for computational vision, CNNs are better than for time data, where probably autoregressive neural network times the transformers are better. So we kind of see that kind of similarities here. And for long range model, like the so-called Sherrington-Kilpatrick spin glass that has, so the prime Hamiltonian has this kind of all-to-all interaction, right? So we found that RNN architectures that have this form, we call it dilated RNN cell, that encode the so-called skip connections that were introduced, basically CNNs to ResNets to deal with problem of vanishing gradient. Here we see that basically it helps to encode long-range correlation that we have in Sherrington-Kilpatrick model. This is the variance of the free energy, variational free energy that I will describe later on. And we see that, yeah, it's way much better than even the tensor RNN. So again, we see that, yeah, depending on the architecture that we use, we have different results on the parameter. So next, I move on to explain actually the core of the variational quantum annealing algorithm. So I motivated this talk by saying that basically annealing paradigm is a search for a complex landscape, either with thermal fluctuation or quantum fluctuations. Another way of seeing it is to see it as an adiabatic evolution, a little bit kind of towards the quantum computing side. So the idea of adiabatic quantum evolution is that you want to prepare your system in an Hamiltonian that is easy to prepare, time evolve it, remove all the quantum fluctuations, and hopefully you find yourself in the ground state of the prime Hamiltonian you are interested in solving. All right, so the idea is also the same here. We initialize the RNN wave function with random weights and biases. So these are energy levels over some parameters. Here is a transverse field. We want to prepare a system in this Hamiltonian at t equals to 0. It's basically you have a transverse field, spins pointing in the x direction. So if this is large enough, all the spins will literally point in the x direction. So to prepare it, we just minimize the variational energy over this Hamiltonian, which is gradient descent. We land on it, very easy. And then we change the Hamiltonian, we time evolve it. We introduce the poem Hamiltonian we're actually trying to solve, right? By using maybe a linear decrease on the transverse field. And when you do that, what happens is that you shoot out of the instantaneous ground state of this Hamiltonian. So you need to come back on it. And to come back on it, we need to minimize what I told before, the variational free energy. And we do that with gradient descent step. We minimize it. And then we change again the transverse field, right? And then we minimize again with gradient descent step, and so on and so forth until when we remove, so at t equals to big T here, this is going to be 0. This is going to just be the Poem Hamiltonian. Hopefully you remain on this lower curve, which is the instantaneous ground state energy through the annealing procedure, whereby you have explored your system, your landscape with quantum fluctuations, and hopefully you find yourself in ground state of whatever Poem Hamiltonian you're interested to solve. We found that the number of gradient distance steps you need to do to remain adiabatic scales with the minimum gap during is bounded by the minimum gap and the minimum gap square during the annealing evolution. So we had a proof of principle with what I mentioned before, but I didn't show you the Hamiltonian. Is the quantum is a chain. You have the spins interacting basically with this interaction that is not disorder here, but you have a transverse field. And this is the expectation value of the Hamiltonian over your ansatz a given time. And here, this is the instantaneous. So you have the exact energy in black. What we call transfer learning is that at every annealing step, every time we change the transverse field, we use the weights and the biases that we learned in the previous steps as an input to the next step. So that's what we call transfer learning of parameters. Whereas at every annealing step, so at every time you change the transverse field or you change the magnitude of the quantum fluctuation in your simulation, if you reinitialize the weights and biases of your RNN, you don't remain adiabatic, you shoot out, you get excited basically, right? So here we've seen that transfer learning as well is something important. Another thing we check is the so-called residual energy. Is just the difference of energy between the ground state estimation we have from algorithm and the exact one, which for 20 spin, we can exactly diagonalize the Hamiltonian and find the ground state. And we see that indeed is always almost close to 0. And this is the gap, the energy difference between the first excited state and the ground state. And indeed, we have very small compared to the gap. So it shows that indeed we can reproduce quantum annealing dynamics using variationally using neural networks. All right. So next, I will talk a bit about the classical annealing formalism, from quantum to classical. So as a recap, we use variational Monte Carlo, a metric, or cost function or loss function, if you want, is this variational free energy that we minimize in this way. For the classical formalism is similar. So instead of this variational energy, we have the variational free energy, right? And this is basically the formula for free energy. Usually you have this internal state minus some temperature, and then you have some entropy, right? And then we statistically, again, evaluate it according to the probability distribution that is represented by our ansatz, and you have this local free energy. So this quantity also is an upper bound to the true free energy, and we can just simply minimize it in the training procedure. All right, so usually this is the prime Hamiltonian you're expected to solve. You take expectation value of the RNN probability distribution. You can use whatever flavor of temperature schedule. Here we just use a simple linear temperature schedule to reduce thermal fluctuation in the system. And here we have the entropy, the so-called von Neumann entropy. And again, if the probability distribution we are sampling over is not normalized, we need to compute the normalization factor here. And yeah, it's just intractable for ansatz that are not normalized to unity. So that's why autoregressive neural network were also more attractive to us. And as a proof of principle, so here what we are showing is the instantaneous variational free energy respect to temperature. It's kind of similar to what we showed before. On the prime Hamiltonian, so we are trying to find the ground state of, this is called the Ising model. It's vanilla model, that standard model that typically people use in condensed model to benchmark stuff. And yeah, so this is a variational free energy expectation value of the samples that are generated with your RNN here, minus the time dependent schedule, and you have your entropy term here that is given by this. All right. And again, for this number of spins, we can compute exactly the free energy. And when we use transfer learning, we see that we indeed can simulate variational classical annealing adiabatically, right? Till t equals to 0. You see, 20 is 0, we are only at the, should be at the ground state of this prime Hamiltonian. No transfer learning, we shoot very, very, very fast out of the instantaneous probability. So here, basically what we are sampling, we are representing at every temperature, the so-called Boltzmann probability distribution, because the Boltzmann probability distribution is a probability distribution of a classical system at finite temperature. And we can see that we can variationally represent it. One thing I would like to mention is that this kind of approach was used in this work, not to solve optimization problem, but to basically find equilibrium properties at finite temperature of some complicated Ising Hamiltonian, but it was used to avoid mode collapse, right? But us, we use here to basically solve optimization problems. Okay, so next, before presenting the results, the main results, I do a recap of the whole variational annealing procedure. So the idea is the following: depending on whether you are using VCA, variational classical annealing, that is the classical annealing flavor of the neural annealing procedure, or you are using variational quantum, that is you're using quantum fluctuation exploration. So typically you set the initial temperature, it has to be high. Remember the example I gave you about metallurgy. You need to hit your material very high. So either temperature or the transverse field need to be so high. And then you train the system initially to equilibrate that value of temperature, that high value of temperature or transverse field via gradient descent steps using Adams, stochastic gradient descent, whatever optimization you want. Okay, so when you reach that system, now you start performing annealing, right? That's where you start exploring your landscape. You change the temperature by some metric that you choose, either temperature for VCA or the transverse field, and you use transfer learning of parameters when you do that. And then you simply repeat 1 and 2. That is, when you change temperature or you change the transverse field, you need to equilibrate again your system via some gradient descent step. And you repeat this until all the thermal fluctuations or all the quantum fluctuations are removed from the systems. And when they are, hopefully, if everything went well, you should find yourself in the ground state of the problem Hamiltonian you're interested to solve. And yeah, and at the end, you can generate an arbitrary number of samples that should give you basically a distribution or solutions to your optimization problems. So that's the variational annealing framework. So maybe I'll stop here if there are questions before I move to some results.
Yeah. Okay.
Yeah, go on.
Go ahead.
Could you define criticality? Excuse me, criticality for the models that you introduced several slides ago. You spoke about at criticality. Could you just make that?
Yeah.
Yeah.
Yeah. Sure. Let me go back. It's coming up. My slides are slow. Okay. Yeah.
Yes,
so
electric. Yeah, that's right.
Yeah, definitely. So for the quantum Ising chain, so the quantum Ising chain is basically a model that represents a magnet, basically a magnet or a material that is magnetic, right? And that basically undergoes some phase transition in the presence of a transverse field, right? So the idea is that when the external transverse field you apply to your magnet is large enough, basically you are polarizing the spins in that material according to the direction of that transverse field. When you reduce it, there is a change in the phase transition in that your material spontaneously has an intrinsic magnetization by the spin inside. That could be either spin up or spin down. So the point where that phase transition occurs is what I call criticality. Right? Yeah, it could be, for example, something that is even more vanilla, transition from water to gas, or something, or from gas to solid. That's what I call critical point, so the point where you have a phase transition. Yes, yes.
Super, thank you very much.
You're welcome. It's typically the hardest point for some systems. Yeah, long range correlations and yeah, things get a little bit crazy. Thanks for the question.
Could you also please re-explain what you meant by transfer learning? You mentioned in your summary slide and also in your plots that without doing that, sort of things don't work properly. But could you please re-explain that?
Definitely. Let's look at these slides. So by transfer learning, what I mean is, so we are training a model, we are training a neural network, right? And the neural networks has, so lambda here represent the sets of weights and biases that I have in my neural network. Okay, so when this value of the transverse field is at a given value in time, I need to train the model to represent the Hamiltonian at that specific value, for example, at 2. When I change it to, for example, 1.8, right? So there are two things I could do. I could either completely reinitialize my model by having, again, random weights and biases for my RNN cell, and again, train the model using gradient descent. If I do that, every time I change the transverse field, this is the curve I get, right? But instead, every time when I change the transverse field, if I use as an input to my model the weights and the biases that were trained in the previous step, this is what I call transfer learning. I kind of transfer the parameters across these different values or across subsequent values of the transverse field.
Okay.
So we check that to show that the encoding the annealing paradigm works. Otherwise, I could always train the model at that value of the transverse field. Probably if I train long enough, I'll probably converge to the right value. Maybe not here, because here things are a little bit difficult. I will show you.
Yeah. Okay.
Things are a little bit difficult, but yeah, but when I transfer, I kind of encode the annealing dynamics.
Okay. Okay, thank you.
You're welcome. Any other question?
My question was answered. Sorry, it's the same question that I just asked. So sorry.
Oh, okay, cool.
Yeah.
Sweet. All right, then I will move on to, I move on to the result, the main result. So the first result we present is variation annealing on randomizing chains. So what are randomizing chains? They are chains, you remember I motivated that we need to have some problem Hamiltonian. And the problem Hamiltonian is basically the optimization problem you're trying to solve. I want to find the ground state of this Hamiltonian. So I have spins, nearest neighbor spins that interact via this interaction term. I consider here two different kind of interaction terms. Either random interaction, where these are just random number drawn between 0 and 1, or there are random numbers that are discrete numbers between plus and minus 1. So this encodes basically the random interaction between the spins. That's what we call random Ising chain, okay? And then the metric checking is expectation value of basically this Hamiltonian over my model, like samples generated by my model, minus the exact one, because for this problem, we actually know what is the ground state, okay? And we check on different lattice sizes from 32 to 128 spins. At the end of the annealing, we generate 1 million samples, and we try about 25 random, we do expectation values of about 25 random realization of the disorder. And yeah, we use tensor, positive tensors RNN here. So first, when we check the residual energy per spin here, respect to N annealing is basically the time we take in changing either the transverse field or temperature, right? If you remember well, I mentioned about a linear annealing schedule, way in which we reduce the temperature. So when N annealing, number of annealing steps, is slow, we are doing some sort of quenching. It's a little bit like you have a block of ice and you just throw it inside a very hot water. You want it to kind of cool down very fast. So you are quenching your system here. You are reducing either the temperature very fast or the transverse field very fast. when annealing is long, you are doing a very gentle and very slow change in either your transverse field or your temperature. It's called kind of the adiabatic regime, where you're very slow. All right. So what we observe here is that at some intermediate values of the number of annealing steps, actually quantum annealing is kind of a little bit superior to variational classical annealing. But at long annealing time, basically classical annealing kind of overcomes quantum annealing. And this was kind of a little bit, and we see it also for discrete disorder here. That was a bit surprising to us because for this same problem, people had implemented classical annealing and quantum annealing using Monte Carlo methods in this paper, and they saw the contrary. Kind of. Still, it's kind of a puzzle to me why on earth this is happening. But yeah, this is kind of what we observe. So maybe we justify it by the fact that since in the loss function of the variational classical annealing, we have an entropy term. So removing entropy for the system maybe helps in the long run. Could be. But it's still, yeah, it's not still clear to us why that. Another thing that was very interesting to us actually is that variational annealing is superior not only to simulated annealing and the real-time dynamic of quantum annealing. That's by real-time dynamic of quantum annealing, I mean, if we take this problem and we run it on an actual quantum computer, because both of them were shown to have a logarithmic scaling, whereas here you see all of these are parallel exponents in the long-range regime. Whereas for simulated annealing implemented with Monte Carlo, and if you run this random Ising chain on, for example, the D-wave machine, like this quantum annealer, it's going to have a logarithmic scaling. So this was kind of surprising to us. But maybe we start having logarithmic scaling if we go to 1,000 spins, could be. But yeah, for these ranges of system size, it was interesting to see that we have a parallel scaling. Right. And that would be motivated for the quantum annealing case. We are doing some sort of imaginary time dynamics of the Schrödinger equation. And we know that imaginary time dynamics is better than real time dynamics. So could be another motivation of why we are seeing better results here. So the next slide is we increase the difficulty of the optimization problem. Now, the problem we are trying to optimize has this form, still disordered, right? But the difference is that now it's on 2D, and it's the so-called Edward Anderson spin glass, and it's known to be harder than 1D chains, right? And here for the 2D, for us to be able to encode the geometry of the prime Hamiltonian, we had to change the autoregressive sampling. Instead of it to be linear, we kind of encode the hidden state kind of takes input from both the horizontal and the vertical line, basically, in the way we do the autoregressive sampling here. Right, and we use still tensorized RNNs with non-weight sharing. So here are the results on 100 spins. So we are comparing a couple of methods here. Again, VCA in blue and VQA. We see that the blue one is superior to the green line like before. So variational classical annealing superior to quantum annealing, which is again surprising compared to previous results. But another thing that is a little bit surprising as well, not so surprising actually, that kind of proves that the annealing paradigm is more efficient to direct optimization, is what we call here CQO. So CQO stands for classical quantum optimization. And it is implemented in the following. So suppose that I only have my optimization plan, my optimization objective function, right? And I really don't care about annealing. I don't care about temperature. I don't care about quantum annealing. I only have this, and I just look at the expectation value of this over my model, right? Over my RNN. So it means that instead of having annealing steps, I only have gradient descent steps. So I only train my RNN by minimizing the expectation value of this function. So these are the red data. After a long annealing time, indeed, your residual energy reduces 10 to the minus 2, so 1% accuracy, but then you plateau even for like 100,000 gradient descent step of training, right? And so this tells you that basically the annealing paradigm is more efficient than just doing direct optimization. That exploring the landscape with thermal or quantum fluctuation, yeah, it's better than just vanilla, like optimization of weight of bias of the direct method. And this makes sense because this model is hard, right? It's hard, so directly optimizing it without using some tricks in the search, it has to be hard. So next, since we've noticed that VCA is kind of superior to, and yeah, so the RVQA is kind of normalized VQA is when we supplemented a fake entropy term to the loss function of quantum annealing. And we see that the entropy term helps, but it's still inferior to the classical annealing one. And probably because it's not a true quantum, it's not the entropy of a true quantum system. It's very hard to have the entropy of a quantum system presented classically on classical computer. Probably that's why we need quantum computers, but yeah, it gives us a hint that when you remove entropy from the loss function, it helps in the optimization. Right. So next, we compare variational classical annealing to standard benchmarks in the community, so-called simulated annealing and simulated quantum annealing, both implemented with Monte Carlo methods on 1600 spins. And here we see that for short annealing times, both of them are superior. Simulated annealing and simulated quantum annealing are superior. And here you can see that simulated annealing, quantum annealing is superior to simulated annealing. But for us, as we increase the number of annealing time, we see that we have up to 3 orders of magnitude better accuracy than the standard benchmark. So it kind of hints to the fact that this variational emulation of the annealing paradigm is more powerful than just mere Monte Carlo. Okay. We tried on another problem, which I kind of hint at in the beginning, the Sheraton Kripat fake spin glass. So the Sheraton Kripat spin glass is just this model of spins that have all-to-all interactions with each other, and the strength of each interaction is random. Right. This is it's actually an empty complete problem, this one. Right. And then, as I mentioned, we found that using this kind of dilated RNN architecture works better for this model. So this is the results that we report here. And again, we see that the tendency is that variational classical annealing is superior to both variational quantum annealing and variational and simulated annealing, and simulated quantum annealing. And so here is 100 spins, again, a million sample at the end of the annealing, 25 realization of the disorder in expectation value here. Okay, so it seems that the autoregressive sampling and entropy probably gives this advantage over Monte Carlo simulation of annealing. Another thing that we checked is we look at histograms, a couple of histograms. So first we sit at this very large annealing 2 to the 14, it's probably around here, 10,000, or this data point here. And we look at the distribution of the solution, right, at that annealing time. We notice that the density of solution, so the lower is better. So this is basically a numerical accuracy. We see that VCA finds way much more solution compared to simulated annealing and simulated quantum annealing. Here it kind of fell into some local minimum, whereas the others, they fall more often in kind of local minimum here. And when we look at, let's say, the 25 instances of, or 25 realization of the Sheraton Kripat model, we look at the probability of success at this annealing time. We notice that basically VCA almost always find the solution with probability of success 1. It's only for one instance. Okay, it's kind of an odd to know. When it doesn't find it, just doesn't find it. Whereas simulated quantum annealing, yeah, the probability is missing some instances and is sometimes lower. Simulated quantum annealing, sorry. Well, simulated annealing always have at least non-zero probability over all the instances, but yeah, some lower than 0.5%. So in general, also in terms of efficiency of probability of success, we see that VCA is more efficient than its Monte Carlo implementation. All right, so this being said, in conclusion, we've seen that an annealing search in the variational landscape seems to outperform like search in the configurational landscape. Like remember motivated searching through this very rogue landscape in the configuration space, but for variational annealing, since basically what we are training is a loss function, right? So we kind of integrate out the configurations, but then we have a loss function, but instead of being configuration is weights and biases, right? So parameters. So it seems that the search is in that kind of landscape, it's more efficient than configuration landscape. We've seen that the classical implementation of variational annealing is more efficient than the quantum one, and it's more efficient than the traditional Monte Carlo implementations. And so we advocate that it's a good candidate to solve real-world optimization problems. All right. And we've also found that there seems to be a rigorous relationship between the INN architecture and the underlying Hamiltonian or the underlying optimization problem that you are trying to solve. And it's a priori not clear what is the choice of the INN architecture you need to have. Seems like it's kind of a trial and error before seeing what works better. So probably good, more research is needed in this kind of direction. All right, with that, I would like to thank my collaborator, first Mohammed, who is a PhD student of Roger Melcom from the Vector Institute and University of Waterloo. He's the machine learning expert. He's the one who wrote all the code for the machine learning models. And Roland, yeah, he has also helped with the simulated quantum annealing simulations, and Roger Melko and Van Kooijskila, who are kind of the PIs. And with that, I thank you for your attention. I will be happy to take more questions.